guys, welcome back. Good to see you. I'm so happy to be here. I'm not a good bed rest person at all, and in fact, I completely failed at that miserably.
Good to have you back.
Yeah. So tests are back there. I wrote that exam the day after I almost died. I was on really high doses of hydrocodone, and it honestly was like the hardest thing I've ever done in my life to write that exam. It took me like 7 hours of like clunking away. And then I came in here and gave it to Andy, who was the person that proctored your test, and I told him to proofread it for me. Apparently didn't do a very good job. So whatever, I did that on hydrocodone, and I don't know what his excuse was. Having 2 number 18s and no number 3. But at least I had 15 questions, so whatever, it worked out. So those are back there, graded. You guys did great, so the median score was a 75%, which is exactly where I want my test to be, is right there in the middle of that C range, because that by definition is average. So I didn't add any points. The homework's back there. I think I missed every due date that I gave for the homework, and I just kept pushing it back and pushing it back. And so just give it to me. I don't even care anymore. I'll still grade it. Some of you had your group name, so you had like, you know, this person, this person, this person written down at the bottom, and maybe not even your last name. And I have no clue who you are. Like, I don't know who in the group it was. I don't know. I tried as best I could going through my grade book to figure out, okay, I don't have grades for this person or this person, so I think this paper belongs to you, and I wrote your name on it. But some of you, I couldn't figure out who the heck's homework it was. So if your paper back there says name and there's just a question mark, that means I don't know whose it is, and so I didn't give you credit. You might want to check that and write your name on it, okay, and give it back to me so that I can give you credit. If you still haven't turned it in, that's fine, I'll take it. Like I said, I missed every single due date. The extra credit is back there as well, so all of those things are in alphabetical order back there. If you haven't already, pick them up after class. Otherwise, I don't keep them because I would have thousands of papers on my desk at the end of the semester, and that drives me nuts. So I will shred them after class if you don't have them. So if you do want them, make sure you get them. Yeah.
So I just had a quick question. So I noticed that you add the extra credit points to the total points for the class on Blackboard.
So there's a column for extra credit, and it's at the very end, and it's a cumulative column. So right now it probably says something like 1 out of 20.
Okay. Because I lowered it by a letter grade for me.
Oh, yeah. So don't look at your total points. So don't even look at that. In fact, usually I take that column out.
I hesitated to even ask.
Right. Usually I take that column out, and I think I'm just going to go do it, because you're not the first person that said that to me.
Well, I know I'm okay with it.
I download everything to Excel, and then I have Excel calculate the grades, and I have to manually add in the extra credit. Otherwise, it looks like it's actually hurting you, because I haven't given you all the extra credit that's available.
I know I'm totally good with it. I assume, but I just wanted to ask.
Yeah, that becomes a problem every semester. I just don't know how to do it differently. Anything else? Don't worry about that. I don't let Blackboard calculate my grades. Okay. Anything else? All right. Well, if not, then what we're going to do today is we'll finish up with chapter 5 and talk a little bit about burns. They're just kind of fun and interesting. Not fun. Interesting to talk about. Okay. And kind of sums together what you guys have already learned about the skin itself. And then we'll go ahead and move into chapter 6 and talk a little bit about bones today, so that again, we're getting matched up with where you guys actually are in lab and kind of keeping these classes neck and neck together, hopefully. Okay. So one of the things that I wanted to say, first of all, about burns is when somebody has a serious burn, there's a couple of problems that arise. And this leads back to what you talked about with the functions of the skin. So you'll remember at the beginning of this chapter with Corey, you probably talked about the skin as a barrier. It's a physical barrier that protects the body, keeps what's inside the body inside, keeps what's outside the body outside. It's a chemical barrier, it's a biological barrier as well. So really it's kind of our first line of defense to keeping our bodies healthy. And so if you think about what happens when you have a serious burn and you've really damaged the skin itself, you're going to have problems keeping things that need to be inside the body. So all of a sudden losing fluids, losing electrolytes through the weeping of those burns is going to become a really severe problem for you, and maybe something that needs to be treated medically if the burn is bad enough, giving you fluids, giving you electrolytes to replace what's lost. But the other thing is, not only does the skin keep what's inside, it keeps what's outside. And we are surrounded by millions of different microorganisms that our skin works very, very well to keep outside of our bodies. And of course, if you lose the skin, if you damage the skin, one of the things that now happens is you've lost that boundary, you've lost that membrane that keeps these things outside, and infection starts to become a really serious problem for you as well. So loss of fluids and electrolytes, okay, the seeping of things that need to stay inside, and also infection, movement of things that are outside, inside to the body. When you lose that barrier, when you lose that membrane, are the two things that become really concerning. Most of you have probably heard a little bit about how burns are classified, and there's some different schema for actually doing this. We're going to talk about just a really simple way that burns are classified, and that is based on severity into first, second, and third degree burns. If you look at these pictures here, you can see a first degree burn at the top. A first degree burn is just a sunburn maybe that we've all had. Here's a second degree burn. Kind of the hallmark of second degree burns are blisters, which you can see in this diagram. So if you've got a burn that's blistered, it's no longer a first degree. It's severe enough to be considered a second degree. And we'll look at the specific reasons why you actually see blistering with a second degree burn. It has to do with the deepness of the burn through the layers of the skin. Here's a third degree burn here. And in the scheme that we're going to use, this is the most severe type of burn. So what we're going to do is spend a little bit of time talking about each of these different burns, the chances of them healing, and also some of the ways that burns are assessed in a clinical setting. And then we'll go ahead and move on into chapter 6, where we're actually looking at the bones. So just a little bit about first degree burns. This is the least severe type of burn. And the reason for that is this is a burn that's not very deep. It's just the epidermis, so from the stratum germinativum up, that's actually damaged with a first degree burn. Most commonly when somebody gets a first degree burn, it's just from sun exposure. So sunburn, as I said previously, is a really good example of this particular type of burn. We've all probably had sunburns, I would imagine, and you know that depending on the severity, sometimes it's a few days, maybe if it's a more severe sunburn, up to a few weeks before these particular types of burns heal. And because it's just the epidermis that's affected, and this is a layer of skin that's constantly regenerating, these particular types of burns don't cause scarring. We've probably, most of us, had the situation where you've gotten a sunburn and it's been severe enough that it's actually blistered. And the reason for that goes back to what's going on in the stratum germinativum. And if you think about that particular layer of skin, that deepest layer of the epidermis, that's where mitosis is occurring. And so you have cells there that are undergoing cell division, and of course to undergo cell division, they've got to replicate their DNA and then divide in half. Well, one of the things that a severe sunburn causes is it causes mutations in those cells in the stratum germinativum that are replicating and are producing new skin cells. So what happens when your skin peels is those cells actually go through a process which is known as apoptosis. They recognize that they have mutations in their DNA, that is problematic, that if they were to continue to divide with those mutations, that could lead to the situation where skin cancer would develop. And so what happens with these cells when you get that type of more severe sunburn that heals is they recognize that those mutations are present, and those cells go ahead and off themselves rather than continuing to divide and produce new skin cells. And then of course you get the situation where the skin starts to peel off in layers as those skin cells are going through apoptosis, through this programmed cell death essentially. So that is a protective thing, but that indicates that you have had a sunburn that has been bad enough that it has done damage to the DNA in these mitotic cells in the stratum germinativum. And that's why having those types of burns that peel really increase your risk of developing skin cancer, because that is a direct indication that you have those mutations introduced and that your body's trying to do the best that it can to actually deal with them and get rid of those mutated cells. But again, it's going to lead to an increased risk of skin cancer. So that's first degree burns. Second degree burns are a little bit more severe. And the reason for that is a second degree burn is a deeper burn. So with a first degree burn, it's just the epidermis that's damaged. With a second degree burn, that burn has penetrated through the epidermis, and actually you have damage to the dermis as well. So that underlying connective tissue is damaged as well. I mentioned previously that with a second degree burn, kind of one of the hallmarks that would allow you to know that you're dealing with a second degree burn is the formation of blisters. So even a sunburn that blisters is a sunburn that's bad enough that it's actually a second degree burn. And at that point, it's not just the epidermis that has been damaged, but it's the dermis as well. The reason that you get blisters, again, goes back to the structure of the skin. So if you think about the skin, you have this underlying layer, the dermis, and sitting atop that, you have a thinner layer, okay, which is the epidermis, and that's something that we should all be pretty familiar with at this point. Well, if you have a second degree burn, you have damage through the epidermis down into the dermis. It's actually the connective tissue in the dermis that's damaged as well. And if you think about the dermis, it's very vascular. There's a lot of blood vessels there and those types of things. So what happens when the dermis is damaged is you start to get fluid leaking out of the dermis. That fluid cannot penetrate through the epidermis to actually leak out of the body. So what happens instead is that fluid builds up. So again, here's the dermis. Fluid's leaking out. That fluid actually builds up kind of at the boundary between the dermis and the epidermis, okay, which is this through here. And you get a blister, which is basically just a bubble containing that fluid that has leaked from the dermis that actually separates those two layers of the skin. And again, that's indicative of a second degree burn because that indicates that the dermis has been damaged as well, and you're starting to see fluid actually leaking from the dermis. When people get a second degree burn, again, it can be caused by a really bad sunburn. I've seen that before. But usually, more commonly, they're caused by exposure to hot objects. And usually it's a 5-second or less exposure to a very hot object that would lead to this type of burn, okay, a second degree burn where the epidermis has been damaged, the dermis has been damaged as well. These types of burns usually will heal, okay, without problems as long as infection doesn't occur. Now, of course, you've damaged the epidermis, you've damaged the dermis, so there's a much more higher risk that infection would occur because you've lost now that membrane, or you've completely destroyed the membrane, or at least damaged the membrane. That would keep things out and keep things in. One of the things that kind of predicts whether or not this type of burn will heal on its own is whether accessory skin structures are damaged. Okay, so things like hair follicles. If hair follicles down in the dermis have been damaged along with the burn, that's where the stem cells are located for actually regenerating skin. And if those stem cells get damaged along with the rest of the dermis, usually this type of burn won't heal on its own because now you've damaged these stem cells that would be able to replace the skin. If it's a small second degree burn, if you don't have those hair follicles and those other accessory skin structures where stem cells are located damaged, then usually this type of burn will heal on its own because the stem cells that would give rise to new skin that would allow the dermis and the epidermis to be regenerated are intact and they're still functional. So sometimes this type of burn heals on its own. Sometimes there's problems with this type of burn healing on its own. The most severe type of burn in the scheme that we're using is what's known as a third degree burn. And the idea behind a third degree burn is you have completely destroyed the skin. So it's not just that it's damaged, it's not just that it's inflamed, but you've had a burn that's actually burned through the thickness of the skin. So the epidermis is gone, the dermis is gone. In some cases, the hypodermis, that underlying layer of fat tissue, may be gone. Sometimes you'll have burning of underlying tissues as well, such as muscles, bones, tendons, ligaments. But if you've got the dermis and epidermis completely destroyed, that's kind of the hallmark of a 3rd-degree burn. And again, this type of burn is usually caused by prolonged exposure to hot objects. So when I'm saying prolonged exposure, that would mean usually a 10-second or more exposure to a hot object to allow for this burn to penetrate through the thickness of the skin. If you look at this picture here, you can see kind of some of the hallmarks of a 3rd-degree burn. So the skin becomes very dry and leathery. Believe it or not, with this type of burn, the burned area itself usually doesn't hurt. Okay? Ideas why? You don't have any nerves. Okay? You burn through everything, including the nerves that would be in the skin that would allow you to sense pain. So very commonly the burned area itself doesn't hurt. Now these areas kind of surrounding the burn that you can see are really inflamed and red where those nerves are intact. That's going to be really painful. But in the burned area itself, we don't have any nerves. They've been totally destroyed, and so there's nothing to pick up those pain sensations. And you can see kind of the color changes that happen as well with this type of burn. And sometimes the skin turns red, sometimes it turns black, sometimes it turns white. You can see all of that kind of here. This obviously is a type of burn that is not going to heal on its own because you've destroyed the dermis, which means that you've destroyed the hair follicles and the accessory structures that are located within it. And so you've destroyed your stem cells that would be able to regenerate skin in this type of burn. So I want to talk a little bit about what we could actually do to treat a 3rd-degree burn, and they can be very, very difficult to treat. But there are some initial steps that need to be taken in order for this type of burn to actually heal. And the first thing is a process which is known as debridement, which is used to remove all of that dead tissue. So there's a lot of different ways that debridement can be done. A lot of times it's done surgically, and they just go in and they remove all of that dead tissue that has been damaged. Also sometimes maggots are used because they'll go in and they'll eat the dead tissue, and they'll leave the living healthy tissue alone. And so they work very good for it, or very well for this debridement process as well. The next thing that's going to happen is, of course, now we've lost this barrier, completely lost it, completely destroyed the epidermis, the dermis, that would keep what's inside our bodies in and would keep what's outside our bodies out. Sorry, I'm waiting for a call from my doctor, and that's probably my husband. I really can't turn my phone off. Sorry. So the next thing that we're going to do is we're going to flood this burned area with antibiotics, okay? Because we're at really high risk for infection because, again, that boundary that keeps everything out has been completely destroyed. And after that, the next thing that we're going to worry about is keeping everything that needs to stay inside as best as we possibly can. So we're going to cover the burned area with a membrane, okay? And that hopefully is going to allow for skin outside of the burned area to grow over that membrane in a lot of cases, kind of absorb it, break it down, and that eventually will lead to healing of that 3rd-degree burn. So I want to talk a little bit about some of the different membrane types that are used with 3rd-degree burns. The first thing that can happen is what's known as an autograft. And if you have had some medical terminology, you know that auto means self or same, essentially. And so what's happening with an autograft is what you can see here. They're going to take healthy skin from an unburned area of your body. If they have a large burned area to cover, they're going to actually mesh that skin to kind of stretch it out. And then they're going to lay your own skin, okay, having been meshed over that burned area with the idea that the skin is going to kind of grow together, and that's going to allow for this burn to be covered, and eventually you're going to have, once again, an intact membrane that's keeping what's outside out and what's keeping what's inside actually in. This is great. This is what we want to do, but the problem is that a lot of times the burned area is so big that it's hard to get enough healthy skin to actually cover that burned area. So in those particular cases, there are some other things that we can try. A homograft essentially is a situation where you take skin from a cadaver, so donor skin basically, and you use that donor skin to cover the burned area. Now that's going to work if you have a large burned area and you don't have enough healthy skin to actually be your own donor. But one of the problems with this, obviously, is now we're transplanting tissues, okay? And you guys probably know, you're familiar with transplants, that there is always the possibility for rejection, and that's true with skin as well. And so that's a problem with a homograft, is that burned skin that's replaced over your burned areas actually could be rejected by the body. So another thing that we try sometimes are skin substitutes, and there's a lot of skin substitutes out there that are used. One of them is actually just the amniotic membrane. So the amniotic membrane is the innermost lining of the placenta. It has been used for over 100 years as kind of a skin substitute in treating these types of burns. And one of the things about it is non-immunogenic. So for whatever reason, okay, and this will make more sense when we get into the immune system, but for whatever reason, the body does not recognize it as something that's foreign, and it does not reject it. So they work all right sometimes. Another thing that we try is what's known as cultured human epithelial tissue. This means essentially that they take a little postage stamp size of your skin, they grow it in laboratory conditions, and they can get it to bath mat size, okay, in a few days to allow you then to get a homograft from yourself, taking just a teeny little bit of skin. They've also developed some artificial membranes. Usually these are made of silicone, polyurethane, nylon, and collagen. And the idea behind these is they just place them over the burned area. That gives you a little bit of a protective membrane so that not as much is weeping out. There's not as much chance for things to come in and cause infection in the body. And then the skin outside of the burned area that's still healthy hopefully will grow over that membrane and absorb that membrane, so you get healing and skin coverage over that area that has been burned so very badly. So those are the things that we try. Burns can be really tricky for the reasons that we've talked about. Oops, I went backwards. Okay. The last thing that I wanted to mention is what's known as the rule of nines. And the rule of nines basically is a scheme that's used clinically to analyze the extent of a burn. And the reason that you would want to do this is for planning purposes. Okay? You need to be able to decide, based on the extent of a burn, what's going to be the best approach for healing this third-degree burn. Can we use an autograft? Is the burned area too large where now we need to look at maybe a homograft, or we need to look at some type of artificial membrane? So that would be the reason for doing this. And then also just planning for fluid and electrolyte replacement, because of course the larger the burned area, the more fluids, the more electrolytes you're going to be losing, and we need to know in a clinical setting how much do we need to replace. Okay, what amount of fluids, what amount of electrolytes do we need to put you on to keep you healthy? So the idea behind the rule of nines essentially is this. It divides the body into different regions, and each of those regions account for 9% or some multiple of 9% of total body area. So you can see how the rule of nines is divided up here. The anterior part of each leg is 9% of the body. Posterior part of each leg is 9% of the body. The posterior trunk is 18%. And so it becomes very easy to very quickly, in a clinical setting, if somebody comes in and they have maybe, what leg is that? Okay, posterior right leg, and the posterior trunk with third-degree burns, add that up, 9% plus 18% is 27% of their body is covered with this type of burn. And that can allow us to say, okay, that's probably too large of a burn. We're not going to use an autograft for that. We're going to have to look at a homograft. We're going to have to look at some type of artificial membrane. But also, that's a pretty extensive burn. That's a very, very large burned area. And that means we're going to need a lot of fluids and a lot of electrolytes replacing because this burn is going to be seeping quite a bit. Yeah?
So, if they take it from somewhere else, aren't you just exposing a different spot?
Skin is very stretchy, and so you can take off a patch of skin and just pull the other skin back and sew it together. It can stretch like you wouldn't believe.
If you know, somebody gets burned or something like that, and it's not over like their entire trunk, let's say, you know, it's only part of the trunk, would they just say then it's 9% of the trunk, or if it's burned at all on the trunk, they consider that 18% of the trunk?
So they would not consider it 18% if it was just this portion of the trunk. They'd probably estimate, okay, if the entire thing is 18%, and we've got a third of that divided up, you know, that just that part that's burned, then, you know, we can add that to the 9% of the leg that was burned or something like that. It's just kind of a really quick guesstimation way of doing things for planning purposes. Whether or not you heal from a 3rd degree burn depends a lot on the extent of the burn and where the burns are actually located. Anytime somebody has burns to the face, the neck, the chest area, that is more worrisome, and the reason for that is you aspirated probably that very, very hot fire, and there's a possibility, a very large likelihood that there's damage to the respiratory passageways. So those burns in those areas are a little bit more worrisome. If you were to have extensive burns, that's really worrisome as well. There was a family maybe 2 years ago that I think was flying in Alaska. They were from Boise, but they crashed in Anchorage. Does anybody remember this? Okay. And the mother had extensive burns basically on her entire underside of her body. And they actually, I don't remember if she died or not. I'm so sorry, I'm terrible. But I do remember that they actually ended up amputating both of her legs because they were having such a hard time keeping fluids and electrolytes in with all that skin missing and preventing infection from occurring. So to try and save her life, it actually was an amputation thing to get rid of that skin that was no longer working as a boundary and get rid of those areas that were leading to fluid loss and actually leading to the risk of infection as well. So serious and tricky to treat, and the more extensive they are and the closer those burns are to the respiratory passageways, usually the worst problem that is going to cause for somebody that's healing from that. Any questions before we move into chapter 6? All right. Give me just a minute to get the notes out of chapter 6. Last year I fell. And the I took my boyfriend, he had to take my and all of a sudden I turned white. And I think most women are just like, whatever.
But then, we were on this way. And then this last year, we went and we were coming back, he was playing off trail, and I just I don't get off trail. And he came upon this guy climbing over the edge. And he had blood all over his face, and I just, I First thing I like, you know, and it's like, I'm fine, but he's not. And they had his, and this guy, it was someone asked me, people have asked me, I just died over things, right? I like he was unconscious. His pulse wasn't good. And everybody after the case, they're like, well, listen, we need to roll him over. And I'm like, no, we don't. We're leaving. That's what makes me well, the minute lifelike, you know, do what's not real. Right, so, but they were, I mean, they got it. I didn't think
All right, guys. So let's go ahead and get started on chapter 6, which is our bones chapter. This is a pretty quick chapter. I just wanted to say a little bit about bones as kind of a general introduction. I think a lot of times they're thought of as this dead thing that's in the body, just this hard thing. What we're going to find out as we go through this chapter is that bones are very much alive. They are very vascular, as you know if you've ever broken a bone. They are innervated, or at least the membranes that surround bones are innervated, as you know if you've ever broken a bone and you felt that pain. There's something that actually is constantly changing within our bodies, so they're not just stagnant, and we don't have the same bones that you had 10 years ago. We're actually constantly breaking down our bones and building up our bones, and it's estimated that about every 10 years you have completely new bone tissue because of that process. So they are very much dynamic, very much living. As you know, if you've broken a bone and you felt that pain and you've seen the swelling and the bleeding that occurs with that type of situation. Most of us have 206 bones in our bodies as adults. There are some variations to that, so you may have talked about a little bit in your lab classes that some people have extra skull bones. That's not that uncommon. They're known as Hermian bones. Some people have bones that develop in joints when they overstress a joint. So for example, it's not uncommon for people that shoot guns a lot to actually get a bone that develops in this tendon right here because they're constantly, it's called a trigger finger, pulling that trigger and really stressing that joint. And having a bone develop there actually helps to relieve pressure on the joint. My mother-in-law had one of those actually develop in her ankle, the patella. Okay, we're not born with a patella actually, and if the next time you see a newborn, squeeze that little skin there and you'll notice it. They don't have a patella, they don't have a kneecap. The kneecap doesn't start to develop until they start walking, and again, then they're putting pressure on that joint, and you get a bone that forms in the tendon to help to relieve pressure on the joint. So we don't all have the same number of bones. Some of us have more than 206. There's probably some of us in this room that have less than 206. When we're born, we actually have far more than that. Newborns are born with about 300 bones because all of their bones haven't fused together at the time that they're born. So you guys know that the skull bones aren't completely fused, but the rest of the bones throughout the body also aren't completely fused in a newborn because all they do is lay there. They don't need those bones to really be supporting them as much as you and I do, who are upright. And what we see then is in the process of development, all the way up to the age of 25. Okay, we've still got bones that are developing, we've still got bones that are fusing together in our bodies, and it's not until about age 25 that we have the adult number of bones, which again in most of us is about 206, but we actually see some variation in that. So we're going to start out with some very, very general anatomical stuff about bone, and then we'll probably have an opportunity to get into a little bit more of bone physiology probably towards the end of today. But the first thing that I wanted to say, just anatomically speaking about bone, is that there are two basic types of bone. So the first of these is what's known as compact bone. Compact bone is also sometimes called cortical bone. It is very dense, it's very hard, it's smooth, it's relatively heavy. As you guys are working with the bones in lab and you look at those skeletons and they look like they're solid, that's because the outside portion of bones are this cortical bone, this dense, hard, smooth bone. If you look at this picture up here, hopefully that is something that looks familiar to you. Okay, this is the skull. So we've got the skull and it's been cut, and you'll notice that the inside of the skull is lined with this compact bone. It's dense, it's hard. The outside of the skull is lined with that dense, hard, compact or cortical bone. But you'll notice right here through the center of the skull, through the middle of this area, we actually have another type of bone which is known as spongy bone. So the other term for spongy bone is cancellous bone. If you look at this picture here, this is spongy bone, a little bit more highly magnified. So you'll notice that it is not solid, it is not dense. The importance of spongy bone is it's going to decrease the weight of bone. So what we see with the bones of the body is we've got this dense, hard, relatively heavy cortical bone on the outside, and then we've got this spongy bone that's lighter, but it's still very strong on the insides of those bones. And that's going to set up the situation where our skeletons are extremely strong, but they are extremely lightweight. Usually your skeleton is about 5% of your body weight. So if you think of yourself, okay, a normal 200-pound man, your skeleton's about 10, 12 pounds actually is all that the bones actually weigh. The bones that you guys work with in lab are not real bones. And the reason for that is real bones are very delicate once they are dried. But if you ever do work with a real bone skeleton, the bones are extremely light. The bones in lab are heavy because they are not real. But our real skeletons are very, very light, very, very strong. Because if you think about those 13 pounds of bone that the average 200-pound male would have in his body, when that average 200-pound male is jumping up and down, he's putting 1,000 pounds of pressure on those bones. Very, very lightweight, but very, very strong. And that's because of this situation where we've got the compact bone on the outside, spongy bone on the inside. We're also going to talk about kind of some mechanical principles a little bit later on in the way that bones are designed that allow them to be very, very strong and to support the skeleton of the body, or to support the body itself. If you look at this spongy bone, you notice it's got a lot of open spaces in it, so it looks like a sponge, and that's where it gets its name from. But then we have these branching bars of bone, which are known as trabeculae. Okay, so that's the term for these bars of bone that kind of connect these open spaces in the spongy bone together. And then, of course, our bodies are as efficient as they possibly can be. And so we've got this open space in here, and the body doesn't ever waste open space. It's going to cram something in there. And what we actually find in the open spaces of spongy bone is a very, very vascular tissue, which is known as red marrow. And it's actually red marrow that produces blood cells. So when we talked about, well, we actually didn't talk about it, so I wasn't here. But in chapter 4, where you saw the notes, and it said that one of the roles of bone is to produce blood cells. That's what the red marrow does. It's a very, very vascular, very bloody tissue. It fills these open spaces, and that's the part of the bone that's actually producing red blood cells and producing white blood cells and producing the platelets, all of the components of the blood itself. So with that having been said, kind of just a very general introduction into bone itself, I want to kind of talk about some stuff that I think you probably did already in your lab classes, and that is talk about the structure of a long bone. Long bones, of course, are bones that are longer than they are wide. So most of the bones in the body are actually long bones, and that's because all of the bones of the appendages, so the arms, the legs, the fingers, okay, the hands, the feet, these are long bones, just bones that are longer than they are wide. So I want to talk a little bit about the general structure of long bones, because that's going to help us to understand when we get into physiology how these bones actually are formed, how they're produced in the body, but it's going to help us to understand also how healing actually occurs, which is the last thing that we're going to talk about in this chapter, which is the healing of broken bones. So some of these terms you should be familiar with from your lab classes. We've got a long bone here. It looks like this is probably the humerus, so the bone in the upper arm. And one of the things that you probably learned in lab is the ends of a long bone are referred to as the epiphyses. Okay, so that's the plural term. Epiphysis would be singular. So when we're looking at a bone, we can talk about the proximal epiphysis, okay, that portion or that end of the bone that's closer to the trunk, and the distal epiphysis. But I'm just wanting you to know basically that epiphysis is the end of the bone itself. Yeah.
So terminology usually epi means above, but with these, it's the top and the bottom side of both of these bones. So is there any particular reason why they're both called?
So I would imagine that it's probably a relative thing. Like this still here is going to be above something else that it's attached into. All right. So we talked about the ends of the bones, and then we've got this portion of the bone through here. You can see this is a very strong part of the bone. It's composed entirely of the compact bone, which is very dense, hard, strong, heavy. That's the shaft of the bone. And the shaft of the bone is also referred to as the diaphysis. If you look at long bones, and this is true basically of all long bones, you'll notice that inside of the shaft, we actually have this open hollow space. And then again, because our bodies are so efficient, we're not going to waste any open hollow space. We use this area of the bone to store stuff, and we'll talk about that a little bit later on. But it may seem kind of counterintuitive as you look at the shaft, which is this portion of the bone that needs to be really strong. It's kind of bearing the load of the bone, to imagine that the inside of that bone is actually completely hollow. And this again gets back to some mechanics that we're going to be talking about that allow bones to be very strong, but also very, very lightweight. And what we're going to see is the way that force is placed on a bone, we need to have a very, very hard, thick outer layer of compact bone, but we can actually have through the shaft of this bone just a hollow opening on the inside without it decreasing the strength of the bone whatsoever because of the way that forces are applied on bones. So we're going to talk about that a little bit later on, but that's how we get away with having this open hollow space through the diaphysis. It's going to decrease the weight of the bone so it's not so heavy, but it is not going to decrease the strength of the bone at all. The strength of the bone is the same even with that hollow because of the way that forces are actually placed on the bone. And we'll look at that a little bit later on. Yeah.
In the picture it shows the yellow bone marrow as like filling the whole thing. Is that how it is?
Yeah, it does. So the only reason that that's been removed up in here is so that you can actually see, oh, there is something that's hollow there. But it would actually be entirely filled with that yellow marrow, which is just fat storage. So basically it's energy storage essentially is what we're doing in those areas of the bone. If you look at the outside of a bone, so we're going to take this little part of the shaft or the diaphysis. We've got it a little bit more highly magnified in this area over here. And with it more highly magnified, you can see that the outside of the bone is covered with this dense tissue, which is known as the periosteum. The periosteum is highly innervated. When you break a bone, that's actually what causes the pain associated with it. Inside the bone itself, we do not have nerves, so that pain is not coming from the broken bone itself. It's coming from damage to the periosteum because this tissue is very, very highly innervated. The periosteum is actually a double-layered membrane on the outer portion of the periosteum. So that's the portion that you can see here in white. It's composed of dense irregular connective tissue. And of course, that's a tissue that's very strong and supportive, but allows for a little bit of give, a little bit of stretch. The inside, so if you focus here where the periosteum's been partially torn away, the inside layer of the periosteum, which is the part that's in contact with the bone itself, this layer is known as the osteogenic layer. And if you break that term down, osteogenic, what that means essentially is the layer from which bone is being generated, okay, or the layer from which bone is being developed. There's a couple of cell types that you may have heard about already that are found within this osteogenic layer. The first of these, this marker stinks. The first of these is what's known as an osteoblast. And osteoblasts are going to become very important in this chapter for kind of understanding how bones are produced. So as you guys may have read already in your lab books, maybe talked about in lab, an osteoblast is a cell that secretes bone, essentially. So the reason that I remember this is I just call them bone builders. And then that helps me because blast has that B sound, and a bone builder, okay, as an osteoblast essentially is the way that I associate them. The other cell that's located in this osteogenic layer is what's known as an osteoclast. And osteoclasts have kind of the opposite role of an osteoblast. An osteoclast, okay, going with my phonetic way of remembering things, is a bone killer, okay, which means that this is a cell that's constantly breaking down bone, and the from the clast and the from the killer helps me to keep an osteoblast essentially straight from an osteoclast. But we've got this situation that's going on in our bones all the time, okay, going on in your bodies right now, where osteoblasts are secreting bone in your body, okay, and osteoclasts are breaking down bone in your body. Why is it that way? I don't know. It's maybe kind of counterintuitive, because why don't we just build a bone and just leave it alone? But that's not actually what we have happening. We have osteoblasts every day building up bone, and osteoclasts every day building down bone, okay, breaking down bone. And we actually have this chemical communication between these two types of cells, where the osteoblasts communicate with the osteoclasts, and they say, we put up this much bone today, so to keep everything normal, stable, you guys need to take down this much bone. So it's kind of like this house in our bodies that's being constantly remodeled, where we're always adding rooms and we're always taking down other rooms so that the house stays the same size, okay, but we're always constantly building it. Why? I don't know. All right. The other thing that I wanted to say, just generally about the periosteum, is sometimes this tissue can start to partially separate from the bone, and when it does, that is one of the causes of shin splints. So shin splints are common, we probably all had them. There are many causes for shin splints, but for those of you that are runners, okay, you probably know that a great way to get shin splints is to run hills. And the reason that that's a great way to get shin splints is because you guys tell what that is? Okay, it's a foot. A great way to get shin splints is to run hills. And the reason for that is when you're running on an incline, the muscles on the back side of your leg are working much more than the muscles on the inside of your leg. And so they are pulling disproportionately on the bone that they're attached to. You're getting more pull on the bone in this direction. And bones, at least living bones, have some give, have some play, have a little bit of flexibility to them. So that bone starts to be bent more in this direction by the muscles that are pulling on it. And as that happens, that can cause the periosteum to start to separate from it to some extent. And that's one of the causes of shin splints, is just that periosteum separating to some extent from the bone itself because of the type of activities that you're doing. So for those of you that are runners, if you do get shin splints from running on an incline, okay, what's the treatment besides ice and those types of things?
Going backwards.
Okay, going backwards, or, I don't know if I can lift my, okay, this kind of stuff. Doing these movements, can everybody see this? Very good balance or anything right now. Okay, these, let's do this. Pretend this is my foot, okay? This type of a movement, because that is now working the muscles on the front side of the leg, so that you're not getting this disproportionate pull between the back side and the front side. So those types of foot lifts, okay, when you have shin splints, can be really helpful, because now they're exercising and kind of isolating those muscles on the front side of the leg so that you don't have that bone being pulled disproportionately in one direction, essentially. If you look at this picture here, you can see that we've got some little stringy structures. These are known as Sharpies fibers. Sharpies fibers are actually what attaches the periosteum into the bone.
These Sharpies fibers actually penetrate into the bone itself. So the periosteum is very tightly attached, very securely attached, because these fibers actually are interwoven with the bone tissue itself. The last thing that I wanted to point out with this particular slide is with the long bone, and this is true with all of the other bones of the skeleton as well, you'll notice that there are areas where we have compact bone, and these are the areas where the bone needs to be very strong. But then we also have areas where there is spongy bone as well. So what we see with a long bone is we've got compact bone, okay, that dense, hard, heavy, very strong bone through the shaft of the bone. And we also have that compact bone on the outside of the epiphysis. So you can see just a small layer of compact bone here on the outside of the epiphysis. What we find on the inside of the epiphyses is we've got that spongy bone, which of course is going to be filled with the red marrow. So within the epiphyses, not as strong of bone, still really quite strong, but more of a lightweight bone. And this is going to be an area, again, within the epiphyses where we actually have that red marrow, which role is to produce blood cells for the body.
Is that why sometimes joints wear out? Because it's not as hard as the shaft?
So joints wear out because of the next thing that I'm going to talk about,
Okay.
which is the articular cartilage. So what we've got at the epiphyses where bones are coming together is outside of that compact bone, and you can see this here in blue. We have a thin layer of hyaline cartilage. So you guys may remember hyaline cartilage from what you talked about in the lab sections is still a relatively strong tissue, but it has more play to it than bone would. And so we see the outsides of bones where they're meeting up in joints with other bones being lined with a layer of this articular cartilage. This is hugely important. So I'll say why and then I'll get your question. The reason that articular cartilage is hugely important is it helps the bones fit together better. It cushions the bones in joints. But most importantly, it reduces the friction in joints, okay? So as I sit here and I move my elbow joint, and I have my humerus and my radius and my ulna that are all moving past each other as I do this particular movement, it's not the bones that are in direct contact with each other, but we've got some hyaline cartilage on the ends of the bones that's lining that joint. And that hyaline cartilage actually makes it, okay, in a healthy joint that's not arthritic, so that the friction of those bones rubbing against each other is 1/6 the friction of ice on ice. So if you can imagine taking 2 ice cubes and rubbing them together, and there would be basically no friction to that, there's 1/6 the level of friction that you would see with 2 ice cubes in your joints as bones move across each other, okay, and everything's healthy, and that's related to this articular cartilage.
Well, you were talking about that being the outside of the bone, and the I can't pronounce any of these words to save my soul, the periosteum or whatever is the outside of the bone.
So periosteum is not bone itself, but it is a membrane. It's a tissue that covers the bone. So it's separate from the bone, but it's kind of a protective wrapping around the bone, essentially. So the cartilage...
It's still outside the bone.
It is. So these areas here through the shaft are all wrapped in that periosteum. Up in here, what we've got on the outermost edge is that articular cartilage. Right.
Oh, okay.
So that's where we're going to find that articular cartilage, is just on those very ends, where they would be forming joints, where they would be coming together with other bones, and that's so that we can reduce the friction as those bones slide past each other, but also cushion them. If you think of directly bone on bone, and that's what happens when people get really arthritic. Bone on bone is not a good situation. Bone is not a good cushioning agent. It's not a good friction reducing agent. And so when you get arthritis and you're bone on bone, that's very, very painful. And it causes a lot of inflammation in the joint. And that's essentially what happens in the most common form of arthritis, which we'll probably talk about when we get to chapter 8. But in the most common form of arthritis that most of us get as we age, the articular cartilage just wears down. Mostly just due to wear and tear. It starts to degrade like all of the other parts of our body. And once that layer of articular cartilage is gone, now you've got bone on bone, which doesn't cushion and doesn't reduce friction, and that's very inflammatory and very painful. Yeah.
your fingers or something, are you like messing with them?
So they
Wives' tale.
honestly, they don't know. It's thought to be an old wives' tale, but they actually don't even know what's happening when you pop your fingers. So there's all sorts of theories about it. One of the theories is you're releasing gases from the joint cavity. So we don't really know exactly what you're doing, what's causing that popping sound. And there haven't been any studies that have shown that it leads to arthritis or that it leads to joint damage. Yeah.
The articular cartilage, does it not rebuild itself when it starts to break down as we age?
Cartilage is very bad at renewing itself because it is avascular essentially. It doesn't have a blood supply, and if you don't have a blood supply, all the things that you would need, like oxygen and nutrients and those types of things, to be able to rebuild yourself are not present. That's why when people have joint injuries like a torn meniscus, you really don't recover well because cartilage does not regenerate. It doesn't replace itself. So, you know, whether it wears out or you injure yourself early on, it causes problems because it's not vascular and it doesn't regenerate. And most of those nutrients, such as glucosamine, have been shown that they don't actually work. That's what the studies are saying, that they don't actually work to help joints.
They don't work or they?
The studies are saying that they don't work. So there was some thoughts for a long period of time that they would because they contain nutrients that are found in cartilage. But if you think about it, you know, cartilage doesn't really have a blood supply. How are those nutrients going to get to the cartilage to help it anyways? And so the studies that have looked at glucosamine and chondroitin and those types of things have shown that that's actually not the case, that they're not actually something that helps with joints. All right. So there's a little structure. This is something that you probably talked about in your lab classes that you'll notice right here. Sometimes with bones, this structure is found between the diaphysis and both epiphyses. More commonly, it's found in just one of the epiphyses. But this is a structure which is known as the epiphyseal line, okay, in adults. So that would be somebody, again, past the age of about 25 when all of their bones have fused and skeletal growth has completed. In somebody younger than that, this structure is known as the epiphyseal plate, or the more common term for it is the growth plate. And the reason that that's the more common term is because I think it gives you more of an indication of what's actually happening at the structure, okay? If you were to look at the bones of a juvenile, what you would find here between the epiphysis and the diaphysis is actually a band of hyaline cartilage, okay? It is not solidified bone. And so you've actually got a joint within the bone itself because you have a band of hyaline cartilage that runs right through it. If any of you have ever broken your growth plate, this is a very, very common break in young people because if you think about a bone, you've got this band of hyaline cartilage through here, that's going to be an area of instability. Hyaline cartilage is not as strong as bone, and so it's very common for children to separate the epiphysis from the diaphysis, and that's what's known as a broken growth plate, essentially. The reason that this area is known as the growth plate is this is the area in a child from which the bone is going to elongate. So what happens in long bones is this situation where we have this hyaline cartilage here. The hyaline cartilage cells go through mitosis, okay, and produce more hyaline cartilage cells, and then the hyaline cartilage is broken down and it's replaced by bone cells. Okay, why? Again, that seems counterintuitive. I don't know. Okay, why we couldn't just secrete bone? I don't know. But the bones like to do things their own way. So this is the area from which the bone is actually going to grow. Okay, is what I want you to take from this idea here. And then we'll talk more about how that happens. We'll look at some actual diagrams of that happening a little bit later on. But that's the reason for the name growth plate. Okay, what we're looking at here is a representation of an adult bone. We have very commonly in labs some adult bones, and so you've probably seen those and seen a little fusion line that runs right between the epiphysis and the diaphysis. When the bone stops growing, what happens essentially is that hyaline cartilage fuses into bone, Okay? And that solidifies the bone all the way through so that you no longer have this cartilage band in the middle of it, the growth plate. What you have instead is just kind of this line, this scar, this remnant of where that growth plate used to be. And for that reason, in an adult, this is called the epiphyseal line. You'll see it. It is very distinct on the bones that we have in lab. So take a peek at those dry bones that you probably looked at last week if you didn't see it then. Yeah.
Is that the process of when you hear people say growing pains?
So growing pains, so here's what the studies have said about growing pains. They are common in children. They usually happen at night. So for those of you that are parents, or I remember getting growing pains when I was a kid, they're kind of this dull ache that happens kind of in the shins area usually. And so it's been kind of this common old wives' tale that it just happens in kids that grow really quickly. And it's the bones that are growing that's actually causing that pain. What the studies have found is that's not it at all. It happens more commonly in kids that are hyperactive, okay? And particularly with my son who's got ADHD that is off the charts. So he used to have growing pains that were just terrible, but I would notice particularly that if he was not wearing shoes and he was running around on a hard surface, like a concrete floor or a tile floor all day, that night I was going to be up all night massaging his legs because that's what seems to actually cause the growing pain. So it's not the growth of the bone itself, but it's hyperactivity and particularly on hard floors with no shoes, putting pressure on the bones leading to that pain at night. That's what the studies have shown.
I think it's kind of like Shin Splints though.
Yeah, I kind of feel like Shin Splints, kind of a little bit, but they usually happen at night.
Well, because if they're on the hard floor, it would stress the bone.
Right, definitely. So if you don't have something that's cushioning and you're putting those forces on the bones, absolutely, it just seems to be a stress thing on the bones is what causes Shin Splints. Did I? Shoot. All right. Anything else? Yeah.
When you're growing, do you have more osteoblasts than osteoclasts, or are they just taking down and building?
They're just taking down and building up at different rates, actually. So we are always taking down and building up, as counterintuitive as that is. And I'm wondering if it's maybe just a nutrients that we're making in the body that we're constantly releasing calcium because we need it, but then we're also constantly, taking in calcium from food and putting that back into the bones. But no, you don't. They just work at different rates, essentially. All right. So we talked a little bit about the medullary cavity already. That's that open space through the diaphysis. Again, it's there. It's going to decrease the weight of the bone because if we had compact bone all the way through the diaphysis, the bones would be much heavier than they are. We want them to be as lightweight as possible. Okay, so it's not really hard to move our bodies, but we need them to be as strong as possible. And I mentioned that we're going to look a little bit later at the mechanics of how forces are actually placed on bones to show you that we can have this open hollow space right through the center of a bone that decreases the weight, but it's not going to decrease the strength. And that gives us this added benefit of kind of having this hollow space within the bone itself, within the diaphysis, where we can now store stuff. And what we do within the medullary cavity essentially is we store a tissue which is known as yellow marrow. I think I mentioned before that yellow marrow is just adipose. It's just fat tissue, so it's basically a nutrient storage reservoir within the bones that our bodies can feed on, that they can use for energy if needed in the future, essentially. If we go back to this picture over here, where we're seeing just that small portion of the diaphysis, a little bit more highly magnified. We've got the medullary cavity through here, some of that yellow marrow, which is just fat storage. What I want you to notice is there is a membrane. Okay, so again, dense irregular connective tissue. It's very similar to the periosteum that sits on the outside of the bone. This membrane is known as the endosteum, and it lines the entire medullary cavity. So just a membrane or a tissue essentially that's covering the medullary cavity and kind of giving it some protection. And the only other thing that I wanted to mention is the red marrow, and I've talked about that already. A very vascular tissue. It has a red appearance to it, hence the name. In the long bones of adults, red marrow is found only in the epiphyses, so it's associated with spongy bone. And of course, it's going to have that role of actually producing blood cells. What we've got in the diaphysis of infants, okay, is actually red marrow all the way through. And if you think about how quickly an infant grows, their demand for blood production is going to be really high. So they've got red marrow in the epiphyses, they've got red marrow through the diaphyses as well as their long bones, all working to produce blood for them. As we age, that red marrow is replaced with the yellow marrow essentially in the medullary cavity. So we've talked a little bit about the structure of long bones, and that kind of builds on some stuff that you guys talked about in lab. I want to mention just briefly the structure of all the other bones in the body. So short bones, okay, which you guys probably talked about in lab, bones that are basically cube-shaped or square, irregular bones like the ribs, the vertebrae, and flat bones as well, okay, which are bones that are just flat like the skull essentially. And with all of these other types of bones, we don't have a medullary cavity, so to speak. We don't have shafts and ends to them, of course. But what we've got essentially is a bone sandwich. So what I mean by that is with short bones, with flat bones, with irregular bones, we've got compact bone, okay, on the outside with a layer of spongy bone through the middle. And of course, that's going to set up a situation where still we've got a bone that's very, very strong. It's lined with the compact bone, but through the middle, we've got the spongy bone. That's going to decrease the weight of the bone, make it so that it's not quite so heavy, but it's still very, very strong. So this is probably the last slide that we'll have a chance to get through today. We've got about 5 minutes left. And what we're going to start moving into here at the end and then pick up with when we meet next time is physiology. We've been talking about just anatomy, how bones are structured, what are the different components of bones, kind of talking a lot about things that you guys have looked at already in your lab classes. And now we're going to switch gears. And the first thing that we're going to start with when we talk about the function of bones, the physiology of bones, is how they're actually produced and how they actually grow in the body. So there is a term, okay, for bone formation, and the term essentially is ossification. When I say ossification, I'm basically talking about the processes in the body by which bone is actually formed. If you look at this picture over here, we have a fetus probably about 8 or 9 weeks development. And of course, all of us, when we're developing in utero, start out as a single cell. And it's not until about 8 or 9 weeks development that we actually get bones starting to form. So this process of ossification, this process of bone formation starts in utero around 2 months. And then that's going to continue, okay, all the way through fetal development, all the way through infancy, childhood, and even into young adulthood, where ossification is finally going to complete about the age of 25 years old. So this is a very long process whereby bones are being formed and bones are maturing actually within our bodies. The last bones actually to completely develop are the clavicles, okay, the collarbones. And because of that, a lot of times those bones can be used to age skeletons. Because if you have somebody that died before about age 25, when those bones would be completely ossified, you could look at the progress in their development, where they're at essentially, and get an idea of the age of that skeleton because they are the last to completely develop. So we are going to talk about a couple of ways that ossification, or this formation of bone, proceeds in humans. The first of these is a process which is known as intramembranous ossification. Okay? So again, intramembranous ossification starts at about 8 weeks development in utero, continues through into adulthood. And this is a process that forms the skull bones. So we can see some intramembranous ossification occurring in this picture here. The only other bones that are primarily formed by intramembranous ossification, again, are the clavicles or the collarbones. Okay? So when we're talking about intramembranous ossification, we're talking really about a process that just occurs with the skull bones and the clavicles. What happens during fetal development is initially we don't have a skeleton at all. Okay? We just start out with cartilage and kind of membranes that are holding everything together. And the skull bones in particular actually start out as a membrane. It's true for the clavicles as well. So it's kind of a dense, thick protective membrane. But what happens, and you can see this process starting in this picture here, is that membrane starts to fill on the inside with bone tissue. If you look at this picture here, in this scan, bone is coming up as red, membrane is coming up as yellow, and you can see how this membrane, okay, that was the original covering and encasing the brain, is starting to fill with bone, and it's starting to harden into bone. And that is essentially the process by which intramembranous ossification occurs. The other type of ossification is what's known as endochondral. So if you break this term down, endo is within, this is referring chondral to cartilage. Okay? So what happens in endochondral ossification, and this is the process or the main process by which all of the other bones of the body are produced, everything but the skull bones and the clavicles. What happens in this process is you start out with hyaline cartilage, kind of a hyaline cartilage model of a bone. And we can see this again starting to occur in this fetus here, where we're seeing red, that's a little bit thicker, denser hyaline cartilage. This baby really doesn't have a lot of bone that's developed yet, but we've got kind of the outlines of the body here. And what happens in endochondral ossification is you start out with a hyaline cartilage model of the bone. Okay, again, this is counterintuitive. The body breaks down that hyaline cartilage model and it replaces it with bone. And again, this is going to start at about 8 weeks fetal development, and that process is going to continue up until about 25 years of age. So you can see this kind of starting to happen here. You can see why newborns are born with way more than the 206 bones that we have as adults, because we've got all these little bone fragments in the different areas of the body that are eventually going to grow together, that are going to fuse together in the adult skeleton. But when a newborn is born, they usually have about 300 bones. They have far more than adult would because they're not quite all yet fused together. So when we come back, okay, we're going to talk in more detail about this process of intramembranous ossification. We'll go step by step. How do you go from kind of this dense fibrous membrane in the skull that's forming the clavicles to actual bone? And then we'll also talk about endochondral ossification. Okay, we'll look step by step. How do you form a long bone from a hyaline cartilage model, break down that hyaline cartilage,